Hi guys, in the last lecture we covered first of all power transformer versus distribution transformer. There I told you power transformer is used in near the generator to step up the voltage for transmission because at higher voltage transmission losses are lesser. And I told you in power transformer full load copper losses are critical, whereas in distribution transformer iron losses are critical. Then we studied harmonics in three phase. There I told you third harmonic current can flow in delta connection or star with a grounded neutral, but it cannot flow in a star with isolated neutral connection. Okay, and fifth and seventh harmonic can flow in any type of transformer connection. Then we studied construction of the transformer. There we saw shell type and core type. In shell type of transformer, third harmonic flux can exist for the star connection and it cannot exist for the delta connection. But in three-limbed core type of transformer, third harmonic current, third harmonic flux does not have any closed path, so flux will be sinusoidal and hence EMF will also be sinusoidal. And last we saw delta-delta connection, in which we saw there were two type of connection that we saw, DD12 and DD6, that is 0 degree phase shift and 180 degree phase shift. Okay, these two type of connections we saw in delta-delta transformer. In this lecture we will cover some more type of connections for the three phase transformer. So let us first start with a star-star connection. Now as you see on both sides all the three windings have a one common point, that is neutral. So this is my star-star connection. All the three windings are connected in star configuration. Again first we will draw the primary phasor and based on that we will draw the secondary phasor. As I told you, this A phase on the primary must always be vertical so that this can be used as a reference phasor to determine the phase shift. So I will draw like this. This will be my A1, this will be A2. Now A1 is connected to B1. Okay, this point is connected to B1 and this phase is A. So B phase will be 120 degree lagging, assuming positive sequence. So it will be like this. This is B1, this will be B2. Now C phase will be 120 degree lagging like this. C2, this will be C1. This all points are neutral. Okay. Now drawing the secondary phasor will be drawn in parallel to the primary phasor. So it will be like this, A2, A1, then A1 is connected to B1 also, it will be B2, then C2, this is C1. Okay. Now this point is neutral on the secondary. Here I am denoting neutral by small n because it is the secondary winding. Now if we denote both the phasors on a clock, A is vertical and small a is something like this. Now since both the phasors are coinciding, we have a 0 degree phase shift, which implies it is a YY12 connection. On the clock it seems as if 12 o'clock is the time, so it will be YY12. Y denotes star and capital for primary, small for the secondary winding. So this type of connection has been named YY connection. Now let us change the secondary connections and try to determine the phase shift. So here I have connected A2, B2 and C2 to the neutral terminal and A1, B1, C1 are free. So again first we will draw the primary phasor. This is A2, then B2, then C2. This will be my neutral point. Now this phasor is going from A1 to A2, but here we are taking output from A1. So we will draw a phasor from A2 to A1. Sorry, A2 to A1. If A1 to A2 is vertically upwards, A2 to A1 will be vertically downwards. Now if we draw B2 to B1, B2 to B1 will be something like this, opposite to this. This is A, B, C. It will be vertically opposite to this. This is B2, this will be B1. then C2 to C1 will be something like this. Okay. What I have done is I have drawn opposite phasors. If this is vertically upwards, opposite will be vertically downwards. If this is like this, opposite will be like this. If this is like this, opposite will be this. Since these phasors were drawn from 1 to 2, secondary phasors will be drawn from 2 to 1 because output is at 1. Okay. Now if we draw both on a clock, A phase is like this, small a is like this. So this connection will be named as YY6. That is, it provides a 180 degree phase shift. Okay. So star-star connection can also provide only two type of phase shift, that is 0 degree and 180 degree. 0 degree is called as YY12 and 180 degree is called as YY6. Okay. So two type of connections are possible in the star-star transformer. Now let us find some features first of all for the star-star transformer. If I take V phase primary by V phase secondary, this will be N primary by N secondary. This can also be written as root 3 V phase primary by root 3 V phase secondary, that is VL primary by VL secondary. So as in a delta-delta connection, here also the line-to-line voltage ratio is same as phase-to-phase voltage ratio. Because root 3 will get cancelled out, so line voltages ratio will same as phase voltage ratio. Now if we keep line voltage as constant, if we say line voltage in delta is same as line voltage in star. So phase voltage in star will be VL by root 3 and phase voltage in delta will be VL. Since it has a lesser phase voltage, so it requires lesser insulation and lesser number of turns. Okay. But if we keep line current same, that is IL star is equal to IL delta, then IP star will be equal to IL by root 3 and IP delta will be IL. So here, IP star will be IL and IP delta will be IL by root 3. So in case of star, phase current is more as compared to delta connection. That means the area of cross section of the conductor will be higher in star connection as compared to delta connection. Okay. So it requires lesser number of turns but the thicker conductors. So thicker conductors will be employed in a star-star transformer as compared to delta-delta transformer. The reverse of this we studied in delta-delta. There I told you that the area of cross section of conductor in delta-delta connection is 57.7% as compared to star-star connection. Here I am just saying the reverse. Star-star connection requires thicker conductors as compared to delta-delta connection. So this type of transformer will be used for high voltage, low current rating. If we keep insulation and area same, this transformer will have higher voltage and lesser current. So it is used for high voltage, low current rating, and it is mechanically more stable. Since it uses thicker conductors, so its balance is better as compared to delta-delta connection. So it is more robust. So this is about the rating and the physical stability of the transformer. Now let us talk about the third harmonics in case of star-star connection. As I told you, in case of three-limbed core type transformer, third harmonic flux cannot exist. Third harmonic flux is absent. That means EMF is sinusoidal. Okay. But in case of shell type, for star connection, we have third harmonic flux. So EMF is non-sinusoidal. Okay. since flux contains third harmonic, so EMF will also have a third harmonic because EMF is nothing but derivative of the flux. So in a shell type transformer with star connection, the third harmonic flux will be present and EMF will be non-sinusoidal. Now let us see what is the effect of third harmonic when we are talking about the star-star connection. The thing is that if we take VAN3 plus VBN3 plus VCN3, I am adding line to neutral voltages of third harmonic for all the three phases. This will be 3Vm sine 3 omega t, okay, which is not equal to 0. Due to which what happens is the potential of this neutral point Vn, it is not equal to 0. Okay, it is called as floating neutral. Okay. Now what will happen is, suppose if I connect a single phase load, then what will happen? This neutral will have a potential with a frequency 3 omega. So this phase to neutral voltage, that is VAN, is oscillating. Okay, it does not have a constant amplitude because of third harmonic present at the neutral. So we cannot connect a single phase load across the star-star transformer. But what happens with the three phase load is, suppose if I want to find line voltage, that is VAB, it will be VAN minus VBN. So if we want to find third harmonic, it will be VAN3 minus VBN3. It will be Vm sine 3 omega t minus Vm sine 3 omega t, which is 0. So line voltage does not contain any third harmonic. So if we are connecting a three phase load, then the voltage across that load will be line voltage, which does not contain any third harmonic. So we can connect any three phase load, that is not an issue. But the thing is, third harmonic voltages are present at the neutral point, due to which neutral is oscillating or floating. So if we connect a single phase load, then the phase voltage will appear across the load which contains the third harmonic. So amplitude of the voltage will not be fixed. Okay, amplitude will be variable, due to which we will have some fluctuation in the load which is undesirable. Again I am repeating, in a star connection, the phase voltage contains third harmonic, but the line voltage does not contain any third harmonic. So when we connect a three phase load, there is no issue because the line voltage has no third harmonic. But if we connect a single phase load, phase voltage will be applied across that load, due to which the phase voltage will be fluctuating due to third harmonic, and the load will experience fluctuations which is undesirable. This is called as floating neutral or the oscillating neutral. So let us see how to remove the third harmonic. As I told you, if we give a grounding connection to the star, then magnetizing current has third harmonic, due to which flux is sinusoidal and EMF will also be sinusoidal. Okay, this is one of the method to remove the third harmonic from the induced EMF or the phase voltage. Other is, we know that delta winding allows the flow of third harmonic current, so there will be no third harmonic flux or EMF. So if we introduce a delta winding, we can remove the third harmonic EMF. How to do that is, first we will have a primary, then we connect a delta in between, then we will have the secondary winding. This is called as tertiary winding. It is delta connected. Now this winding will allow the flow of third harmonic current in phase, due to which there will be no third harmonic EMF induced in the phase voltage. Since there will be no third harmonic EMF, the single phase voltage will be sinusoidal and we can connect the single phase load to the transformer. So it is by introducing a third winding, it is called as three winding transformer. Third winding is called as tertiary, which is present between primary and the secondary stage. Okay. So this way also we can make the EMF sinusoidal. Tertiary winding will take the third harmonic magnetizing current, so EMF will be sinusoidal. Okay, this is how we can remove. Other purpose of tertiary winding can be, if we connect capacitors across it, then we can do power factor improvement. This power factor correction we will cover in power systems, but by connecting the capacitors we can improve the power factor, that is we can make it closer to unity. So that is done by connecting the capacitors across the tertiary. Because primary will have source connected, secondary will have load connected, but tertiary winding is free. So we can connect capacitors across the tertiary winding to improve the power factor of the system. Okay. So this is all about my star-star connection. So what do we study? We saw that there are two connections possible. One provides 0 degree phase shift, other provides 180 degree phase shift. Then we saw that star-star connection has same line-to-line voltage ratio as the phase-to-phase voltage ratio. It requires thicker conductors. It requires lesser number of turns. It is used for high voltage, low current applications. And last we saw that third harmonic currents will be present in case of delta connection. So EMF will be sinusoidal. Third harmonic current will be absent for star connection. So EMF will be non-sinusoidal. And how to remove this? By grounding the neutral or by connecting a tertiary winding. Otherwise the neutral point is floating, due to which load experiences fluctuation in the voltage. So we cannot connect a single phase load across a star-star transformer. Let's move on to our next connection, which is delta star transformer. Okay. The procedure is same to draw the phasor. First we will draw the primary phasor, then only the secondary. While drawing the primary phasor, my main objective is that this capital A phase should always be vertical. So how to draw? First let me draw A phase. Let us say this is A1 to A2. I am drawing phases like this. This is A, this is B, then this is C. Then A1 is connected to B2. B phase is like this. A1 is connected to B2. This will be B1. B1 is connected to C2. C phase is like this. This will be C1. Now let us draw the secondary phasor. A1 to A2 will be like this. Then B1 to B2 will be like this. Then C1 to C2 will be like this. Okay. So if we draw the reference phasor in the primary winding, first of all I will remove the 1 terminals because output is taken at 2. Now the point touching the A2 will be A, B, C. As you can see, the reference phasor of A is vertical. So I will draw A like this. Then small a will be like this. Now this angle is 120, so this angle will be 30. So if you see, it is like 11 is in the time in the clock, so it will be called as dy11. D means delta, y means star. So it will be a dy11 type of connection. Okay. Just you need to make sure whenever we have a delta connection on the primary phasor should be vertically upwards so that it can act as a reference phasor. Next, let us change the secondary connections. So I will draw primary as it is. A2, B2, then C2. Okay. Then A1 to, now we have to draw A2 to A1. A2 to A1 will be opposite of that A1 to A2. This is A2 to A1. Then B2 to B1 will be also opposite. B2 to B1. C2 to C1 will also be opposite like this. Sorry, B2 to B1, C2 to C1. This is my A phase, B phase and C phase. Now if we draw reference phasor here, it will be A, B, C. If we plot these on a clock, A is like this and small a is like this. So the time on the clock is 5. So it will be called as dy5 type of connection. Okay. Because the angle between the phasors is 150 degree. So it is a dy5 connection. So what does it provide? It provides 150 degree lag. Okay, because it is clockwise, so it is lagging, so 150-degree lag. In our previous connection, what was the case? It is anti-clockwise by 30 degrees, so it is 30-degree lead. Now let us change the primary connection. If we change the primary connection, here A1 to A2, first of all we have to draw A1 to A2. Let us draw like this, A1 to A2. Now A2 is connected to B1. B1 to B2 will be like this. Okay, because I am taking A, B, C. So B1 to B2 will be horizontal and A2 is connected to B1. C1 to C2 will be like this. Okay. But now if you see, A2 is lying here. It is not vertical. So let us rotate the triangle. If we rotate the triangle, it will be like this. This will be my A1 to A2. This will be my B1 to B2. This will be my C1 to C2. Okay. In any case, you have to make sure that A2 lies at the top. Okay. This we need to make sure. So whatever triangle you draw, you can rotate it in such a manner that A2 lies at the top. Okay. Now here A2 is lying at the top. Then we will draw the secondary phasor. A2 to A1 will be opposite to A1 to A2. It will be like this. A2 to A1. Then B2 to B1 will be opposite of this. This will be B2 to B1. C2 to C1 will be opposite like this. So if we draw now on a clock, first we will draw reference phasors in the primary. It will be A, B and C. So A is vertical and small a is like this. So this connection will be dy7. It is as if 7 o'clock is in the time. So it will be a dy7 type of connection. Is it fine? So remember, no matter what primary triangle you draw, you have to take care of two things. First of all, you are taking a positive phase sequence, that is ABC. Then after you arrive at the triangle, make sure that A2 lies at the top. How to make sure? You can rotate the triangle clockwise or anti-clockwise so that you end up in this position. Then only draw the secondary phasors based on primary phasor. If primary phasor is A1 to A2, secondary phasor is A2 to A1, they will be opposite. If primary phasor is A1 to A2, secondary is also A1 to A2, they will be in same phase. Okay. So let us try this connection. Now here again I have changed the secondary. So primary phasor will remain same. This will be A1 to A2. This will be B1 to B2. This will be C1 to C2. Okay, I have directly drawn this triangle just to make sure that A2 lies vertically upwards. Now the secondary phasor is also A1 to A2. It will be like this. Then B1 to B2 will be like this. C1 to C2 will be horizontal. It will be like this. So if we plot it on a clock, first of all we will need reference phasors A, B, C. A is vertically upwards, small a is like this. So it is as if 1 o'clock is the time, so it will be dy1. So it provides a 30-degree lag. So we have seen that this transformer can provide 4 types of phase shift: plus minus 150 degree and plus minus 30 degree. These are the possible phase shift with the delta star connection. Okay. And if we take the line to line voltage ratio, VL primary by VL secondary, it will be VL primary will be same as V phase primary because it is delta, but VL secondary will be root 3 V phase secondary, which is 1 by root 3 into NP by NS. So phase voltage ratio is not same as line to line voltage ratio for the delta star type of transformer. Okay. And we can see that V line star is equal to root 3 into Ns by Np into V line primary. Okay. So here a factor of root 3 is coming. That means the secondary voltage is higher as compared to the star star or the delta delta connection. Because in star star connection or delta delta, we saw VLS by VLP is equal to Ns by Np. But here root 3 is additional, so it has a higher secondary voltage. So it can be used as a step up type of transformer. Okay. It has a higher secondary voltage, so it can be used to step up the voltage. It is used as a step up transformer. Okay. But if we keep the voltage same, then the number of turns would be lesser. So here for the same number of turns we are getting a higher voltage. So to keep the voltage same, the number of turns required will be lesser. Okay. So for the same voltage rating, delta star type of transformer requires lesser number of turns as compared to delta delta or the star star type of transformer. Also here the secondary winding is delta. Sorry, primary is delta, which can allow the flow of third harmonic magnetizing current. Due to third harmonic magnetizing current, the flux will be sinusoidal and EMF will also be sinusoidal. So now you can supply a 3-phase load as well as a single phase load. There is no problem of the oscillating neutral. So remember, if ever you want to get a EMF which is sinusoidal, you need one of the windings to be delta connected, because delta will allow the flow of third harmonic magnetizing current and EMF will turn out to be sinusoidal. So if primary or the secondary winding is delta connected, the problem of third harmonic EMF is resolved. So these are the features of the delta star type of transformer. What you have to remember is the phase shifts plus minus 150 plus minus 30, and it can be used as a step up transformer because of the highest secondary voltage. So let us summarize what we learned. We saw star star connection. There we saw two type of phase shift, 0 degree and 180 degree. So we saw YY 12 and YY 6. Then we saw delta star. There we saw 4 type of phase shift, plus minus 150 degree, plus minus 30 degree. It can be used as a step up transformer. And we saw in star star connection, due to problem of third harmonics, we saw the concept of tertiary winding, which can be used for power factor improvement as well as removal of third harmonics, because it is delta connected. Okay. Due to delta connection, it allows the flow of third harmonic magnetizing current, so that flux is sinusoidal and EMF is also sinusoidal. These are the features of star star and the delta star transformer. In our next lecture, we will cover some more connections of the 3-phase transformer, and then we will see some problems based on this.